and it is increasing day by day. So these are some of the well-known actually school level means observations, and the need for exploiting or harvesting the renewable energy sources, and to reduce the grid independency and so on, because for a country like India, where more than 65 approximately are basically being catered by the thermal power plants, and which are again, these are fossil fuel based, and these are some of the consolidated projections, and how this renewable energy means, just a second, I will take a marker. Okay. So here some studies actually report even, yeah. So I told 60, but it is actually 20, 52, what maybe, but more than half are actually being fulfilled by the thermal power plant, and we can see that this renewable sector is not. So there are there are challenges also, but at the same time, the research which needs to be done, actually this has not been up to the mark, to say the least. So there are and one of the key areas is the waste management. So nevertheless, if we talk about waste management, so because the staple food in India is, say, agriculture, say rice and wheat, but again this basic this biomass, which is basically generated from those agrarian resources, these are also not so well managed, to say the least. So this is the energy demand, how it has to be fulfilled, and yeah. So these are some of the energy sources which can be even found by. So we have been working on this. A few things like solar ponds. So this is not the main theme of the discussion today because of the shortage of time. So I'll just focus some of the applications of biomass gasification and what we have done here, and it's how to improve, and also some suggestions are also welcome. And yeah, so this is one of the things. So we can witness in our day-to-day life, and even in remote villages. So these are some of the practice nearby village at IIT Ropar. So these are not taken from any other published literature or anything. So only the graph is being made, and these are real fields. Whenever the harvesting of the crop is actually taking place, so the farmers basically set aside this field, and these are creating stubble burning, and maybe the disposal related problem, and also many environmental issues. So this is one of the videos which my student has actually taken. So I would like to play it, and you see. So this is just outside the IIT Ropar campus. So our campus is actually located in a very pristine location, and so this is the condition. This is the condition, and I think. Since it was taken after the COVID itself, and so these are the problems. So these are the problems. So especially in Punjab and maybe the northern sector, and I'm sure more or less it is taking place throughout the country. So because the farmers, they want their preparing the soil as soon as possible, and this disposal of these wastes are actually challenges. And in the Times of India, sometimes back, so these are some of the real-time data, and how much is being generated, the paddy residue, and wheat and sugarcane. These are some additional things. So these are some of the problems. Yes, so for our next generation, for children in particular, so a lot of actually these things are there. Now, what we have been doing. So these these pics basically show some of the fields condition, and these are some of the wooden scraps, and these are our paddy straw. So since time is short, so I will just go through the main theme of the techniques which we are following, and how we are basically utilizing it for our useful purpose. So first is the biomass gasification. Now there are a lot of actually biomass. So before that, since the student is a PhD scholar or maybe a master's scholar, so some basic analysis as far as the theoretical studies are concerned, and each of us might be knowing. So these are nothing but the various analysis like ultimate analysis, proximate analysis, and so on. So these can be actually done. So this is our biomass gasifier setup, and yeah. So this is our biomass gasifier setup. So this is a downdraft type of biomass gasifier, which consists of a hopper, and it has some zones like drying zone, and then a reduction zone, combustion zone, and so on. So this process produces syngas, and this syngas, we know that it is mainly composed of hydrogen and the methane as the constituents, and there are a lot of filters to clean this thing. So we have this setup, and we have another setup of this is of 10 kilowatt electrical capacity. So this is over one engine is here. Now question comes that if we are using a gas and if we are doing combustion, so still we cannot eliminate the carbon dioxide completely, these greenhouse gases. But the advantage is that the emission which is taking place, even if after, if it is, because this genset is like something like a diesel generator, but it is not operated with diesel, it is operated with a syngas, that is like this. So we have conducted a small study on this red mulberry, because this is known as a shatooth at our place. So those dead branches and other things, we have studied it, and this was published sometimes back. And so this is the one of the techniques. Just so these are the characterization. So we can do the characterization even at our lab, and if some resources are not there, so there are a lot of other institutes and research organizations like CSIR and even some other universities. So these ultimate, proximate, and higher rating values and other things. So these are the standard formula. So in case of anything, if you require, you can please feel free to contact at my email address shown at the first page. So these are the things. Now, so these are the technical things. Okay, stoichiometric air fuel ratio, how much it is, then what is the biomass consumption rate, and what is the actual air fuel ratio. And there is something called equivalence ratio. That is something like fuel to gas ratio. So air to so cold gas efficiency and so on. And these are some of the basically standard analysis, like we take a set of data, statistical analysis. So these are a part of, we can say, a typical basically a thesis, or just a second, I think some message is coming. Let me check it. Just a second. Okay. I think some message was coming. So anyway, so I think I can go ahead. Okay, so these are some of the uncertainties, and also these are part of a typical actually research paper, and means it may appear that the practical aspects are not basically quite evident for a student, say maybe an undergraduate level student, or maybe in the beginning part of his research. So these are the flame quality. So in the gas thing, the biomass setup, there is a provision also of a burner, so we can have a bypass. And this was basically custom made by one of our projects, and we can see that the operation.
Excuse me, sir.
Pardon?
Sir, previous slide, you are explaining about the uncertainty test, I think so. Is it?
Yes.
Can you give elaborating little bit? Because we are suffering for that.
No, it's okay. You're free to contact me or any of my students. See, this is basically. I will just spend 2 minutes then. This is nothing, because, for example, we measure power. Okay, we measure power, and say power is nothing but 2 pi nt by 60.
Yes, sir.
Correct. So obviously. So here, say theta will represent a power. Just I am saying an example, small example, because there are a lot of actually measured variables. So if my output variable is theta, so for instance, say power. So theta is power, and it's a function of n and t. 2 pi and T by 60. Now N is measured with the help of, say, a tachometer. Well, and T can be found by, say, load and the distance and those movement and other things. So there is a weighing balance. It may be either of a digital type or an analog type. Well, so always there is an uncertainty in the individual measurement because there is a least count. Even if we take a vernier caliper or if we take a micrometer, maybe a digital sensor, so there is some uncertainty. Like we don't have, for example, scale. In engineering drawing we are using. So there we can say that the least count is, say, 1 mm. Well, 1 mm. So if a reading is between 1 and 2 mm, so we are not certain about that reading. Well, so that is based on the least count. So there are certain uncertainties always, even in the digital media, for example, say voltage or current characteristics. So there is some least count. So the uncertainty in individual measurement, how it is propagated, and it is affecting that power. So uncertainty in power, it is nothing but we just take the derivative and u y1. That means the individual uncertainty in that particular instrument, and u y2 is nothing but individual uncertainty in my second experiment. So this is pretty simple. Basically, it is. Means I would suggest you just to have a look at a book, because there are a lot of books. One is by J.P. Holman, that experimental method. There is also a very beautiful book, and Professor S.P. Venkatesan. Any of the measurements and instrumentation book. So this is the basically Moffat's equation basically. So am I clear, or means if required, I can explain you with a pen and paper also sometime. No? So these things can be actually differentiated, right? Because dp by dn, say del p by del n into uncertainty in n. Suppose uncertainty in n is about maybe 10 rpm, so that will be 10 over here. Yes, and similarly uncertainty in, say, load, it is, say, 0.5 kg. So y2 will be, say, 0.5, and that is we can differentiate because this is a mathematical expression. So I think it is quite obvious, and there is not much difficulty in evaluating this. Then what we do is that the various actually these equivalence ratios. So if the this thing is not optimum, that means my air supply to the biomass engine or the gasifier, it is not optimum. We can see that there can be due to the soot particles, or maybe due to the excess burning of the N2. So the flame quality may not be a fully bluish flame, but at an optimum we can get, and that is quite evident by seeing the trends of the average calorific values and the cold gas efficiencies, where these are the trends. So we have to basically operate the biomass gasifier over this region. Now these are certain comparisons we made for our biomass, and it is quite decent. It may be superior to some of the studies, but it may not be that much up to some of the studies, but this can be a suitable thing. Now these are some of the trends, which again I am not explaining each and these things because of a little bit lack of the time. So we studied 3 types of biomass. One is the dried grass, leaves, and dead branches. So not only it helps to basically clean the nearby campus, basically, fortunately, and also it can lead to some of the production. And that place where I shown you that we don't have any grid-based electricity connection. So every power and other requirements we are fulfilling by either solar and or maybe the biomass thing. And of course, a battery storage that I will just discuss. So this thing, this is the concept which we implemented. It was published, as we can see, that in one of the good international journals. So what we actually demonstrated is that after, say, it has generated some power. Now the exhaust flue gases, it will be emerging out of the biomass gasifier, and it is at a very high temperature. So why to waste that energy and not utilize the same for some useful purpose. So here we have used a thermoelectric generator, and these are thermosiphons. Now, these TEGs, these have some maximum temperature sustaining limit, maybe 150 or maybe up to 200 degrees centigrade. But these gases are very high temperatures, at a very high temperatures, like of the order of maybe 500 or maybe 450 to 500, like that. So it's very high. So we cannot directly utilize that. So what we did is we have kept two containers of water, and we are basically heating the water to some temperature which are basically lesser than that, but it may be so that this temperature may be well below even 100 degrees centigrade. So so what we did, we created a thermosiphon here, so that maybe at around 670 or 80 degrees centigrade the water actually boils within the system, and that is a vacuum pipe, vacuum type of sort of a heat pipe arrangement. And we have affixed a series of TEGs. So there are two containers we have basically demonstrated, and it can actually through the Seebeck effect, because there will be a condensation at its upper section, and the hot media, or this is the source tank, this is the bottom one, and the topmost one is the sink tank. So the working fluid, it may be a refrigerant or maybe even distilled water, it can actually evaporate and vaporize, and it can when it comes to the contact with the cooler junction, it actually releases the heat. So this is the concept, and this is the port for creating the vacuum inside the this thing. And these are the TEGs. So we have considered the bismuth telluride, and with the specifications shown over here. And yeah, so these are the basically principle of this, again the thermosiphon, how we have basically made, and for what application. So these are the typical actually voltage current characteristics, and the temperature over time, how the source temperature is basically changing. So these are some of, and the variation of the load and on the current and output voltage. So these are again sort of and the conversion efficiency, and well, this conversion efficiency is not very high TEGs, so there is a opportunity to actually do work or carry out work in exploring various semiconductor materials, but that was not a direct purview of our work. Our work was more like application oriented, and these characteristics we have basically studied at different filling ratios. That means we are varying the amount of working fluid within the thermosiphon within this range, and there is certainly a optimum basically TFR, beyond which the performance is not so actually good. And this is a demonstration of our so this is a typical basically battery basically recharging thing, because the current at the current that is being produced by the thermoelectric generator, well, this is, even though it is not quite high, but still it can be basically used. And this is one of my scholars who was working in a project, and these are the current characteristics, voltage and current, all these things, and this is the variation of the load by a rheostat, and using that we can get those basically graphs. So this is one of the process. And then next I will show you that for what purpose we can use that electricity. So we can use for a plenty of application. First we can use it for charging a small UPS battery, which are used in many places at our day-to-day observations. And we can also power the battery banks in a typical basically say in a computer platform or any other thing. So these are some small scale applications, because see, the power which was generated using the thermosiphon based setup, this was not very high. Well, so we want to use it for a little bit more scale applications, large scale applications. So why not we get rid of those vacuum and other things, and let us actually try to derive more power. So we have devised a small heat exchanger like this, which can accommodate more number of TEGs, so that it can generate more power, and in that process we can even recharge a battery of a high capacity. For example, a automobile battery, or maybe a inverter battery of our typical house. And this is a small scale solar pond. Again, due to shortage of time, I'm not discussing this thing, but this is also a waste heat recovery system. We can directly utilize that water also, but solar means we are basically reducing the load on this particular biomass engine, so that during the daytime, when the solar energy is available. So this is our basically experimental facility, and you can see there is no basically grid and other connections. It is completely whatever the fan, and if any lights are there for night working. So these are basically managed with the help of the gasifier. So one gasifier is over here, and another is located at its back. We can see the only partial view, and that was used to power. I will just discuss that setup also for air conditioning purpose, for a small test chamber shown over here. Well, so these are some of the basically voltage, current, and other characteristics. So further discussion can be found in our research paper, and this was the battery, which was basically recharged using the thermoelectric generator and maybe the heat exchanger. So this particular work is still under review in one of the journals, and we have got the comments recently, and these are positive. So we hope that soon we will be having this online. Now this is a biomass gasifier working. I have intentionally, yeah, so it is quite noisy, so I am putting it in mute mode, because we have removed the silencer. The noise is because we have moved the silencer for the waste heat recovery, but if we put the silencer, it is not that much noisy. So just a second. So this is okay. So this is the setup. So this is the setup, and just I will lower the voice little bit, so that, yeah. So this is these are the basically typical components of the gas generation, because gas needs to be cooled also. Otherwise, if it is the hot gas is supplied, cooled and as well as cleaned. So these are the filters basically for cleaning of the syngas. And this is the typical engine which is being run, and these are the control panels for monitoring the setup. And this is our setup. This is the typical setup, and this is the solar pond. So there are a lot of actually work on this for extracting the thermal energy from solar ponds, and these are the typical temperature variations in the control panel. So this is in a nutshell. Another application, actually, this is the last of the applications, and this is for the purpose of, say, as I told you. So I will just so this is for the purpose of air conditioning system. So we have developed a small scale absorption based. So this is the novelty, and recently that has been submitted for a patenting, and we can see how it is completely operated with the help of renewable energy. So absorption system, we know that we require hot water or some thermal energy source, and so these are some of the FCU means a fan coil unit. So just a second, sorry, this is not so. And the temperature reduction that we have basically attained, and this is the genset basically. So yeah, and this is the another gasifier which is of this is done by another scholar. He has actually defended the thesis recently, and yeah, so this is the same genset but used for air conditioning purpose. and this is the gasifier. So the main thing, I will not spend much time. The temperature that we now we have inside the room, we have generated the artificial load by some problem is there with the video. I don't know start or not. So about 10 degrees uh, reduction we have achieved using this setup. And I'm sorry, this thing is hanged. Just a second. Just a second. I will not spend much time, but just a second. Yeah, so I will directly open the video rather. This is fine. Yeah, so this is the load generation. This is the process of load generation, and this is the FCU. This is the FCU means for fan coil unit of a typical air conditioner. And room air temperature, when we started, we can see that it was about 33 or something like that, or maybe a little bit more. Let me check it. So this is test room with the load generation. We have used many bulbs basically, and the chamber was totally insulated from outside. This is the test chamber, and room air temperature, it was say 32.8, and this is the chilled water temperature reduction. And this technique is eminently used for even large scale air conditioning. And you see now the temperature of the chilled water is reducing. It is reducing. We have achieved up to maybe, I think, 15 degrees centigrade probably. And yeah, so this is the before the experiment. The temperature was about 36.5 degrees centigrade. And when we supplied that, and it is fully basically renewable energy assisted. And these are various sensors which are basically located. So this was outdoor air temperature, and chilled water temperature, now it is increasing because now this chilled water temperature is being sent to the room, which basically gains the latent as well as the sensible heat from the indoor space. And yeah, so now we will see that now it is increasing basically gradually. And let us so this was also supported by one of the DST projects, and finally we can see that it is about 27, so nearly roughly 27.6. So roughly we achieved about 9.5 to 10 degree temperature reduction. Of course, there are more scopes for improvement, and we are still working on those actually addressing the problems. And finally, I would like to conclude my talk. And nevertheless, these funding agencies, our institute and the DST and the SERB and CPRI, and I have not mentioned the names of my students basically because there are a lot of students at UG, PG, and even at PhD level. There are a lot of collaborators. So I'm sorry I could not actually list all of them's name. But majorly the money has been obtained from there. And so this is the small work which we have done. I have tried to consolidate it in a best possible